Hello dear students, good morning all of you. Today again we are going to discuss organic photochemistry. And in the previous video I have discussed the main importance of organic photochemistry in our day-to-day life, why it is playing an important role in the sustenance of the life, sustaining our life and even the sustaining the creation. And we also discussed three important basic laws that are governing the photochemistry, that is Grothus-Draper law, Stark-Einstein's law, Beer-Lambert's law. Okay, after having discussed the basics of organic photochemistry, we are going a little more detailed into the basics. What is happening to the organic molecule when it absorbs energy in the region of UV visible? And what is happening to a molecule before absorbing the energy and after absorbing the energy? And which molecule will be giving the product? Whether it is the organic molecule which did not absorb the energy, or the organic molecule which has absorbed the energy. And what happens to the electrons that are present in the organic molecule? And if electron is having that much sufficient energy, what type of an excitation that electron takes, that electron is going through? And what happens to the stereochemistry of the product that is coming to us? And these are some important topics we will be discussing in today's class. So we are still in basics of photochemistry. So we know that for a photochemical reaction to take place, the light energy is very, very important. The first law, Grothus-Draper law, says that light must be absorbed by the chemical substance to undergo photochemical reaction. So an organic molecule, all of us know that this organic molecule absorbs energy, that is H nu, and becomes an organic molecule of excited state, and that molecule will be giving us the product. Most of the times, almost 90% of the photochemical reactions, the product is obtained from an organic molecule from the excited state. Now we will be going to the details. What is this energy? What is the light that is absorbed by the organic molecule? We need to study the main type of light that is absorbed by the organic molecule, because Stark-Einstein's law says that one molecule will absorb only one quantum of energy. That is, for each photon of light absorbed by a chemical system, only one molecule is activated. So we will be going in detail to these laws and what is happening to this organic molecule. The energy for a photochemical reaction in a photochemical process is absorption by the electromagnetic radiation. That means the chemical substance to undergo photochemical reaction, it has to absorb energy in the form of light, not in the form of heat. Organic molecules. Now, all the organic molecules, suppose if you have an organic molecule, it has to undergo a photochemical reaction, absorbs light in the H nu and becomes an excited molecule. And this only will give you the product. Now what is this H nu? What is this H nu? H nu is actually light energy. Light, an ordinary light if you take. And what is this ordinary light? This ordinary light is an electromagnetic radiation. A radiation which is associated with both the electric field and magnetic field, and they both are perpendicular to each other. They both are perpendicular to each other. For example, if you take light, okay, if you take light, This can be a magnetic field. Then we can draw electric field also. We can draw an electric field also. Let me take another color. See, now earlier that light has only x direction, now y direction and z direction. So this is called electromagnetic radiation. And this electromagnetic radiation, the light will not, the organic molecule will not absorb energy from all the radiations. It will absorb energy only from the UV visible region. It will absorb energy only from the UV visible region. That means for a molecule to undergo a photochemical process, it has to absorb electromagnetic radiation, but not all the frequencies. It is absorbing a corresponding frequency, that is from the UV visible region. We will be speaking in the wavelength terms. UV visible region means in the electromagnetic radiation, where the radiation is a combination of radio frequency rays, microwave rays, infrared rays, ultraviolet, UV, then X-rays and gamma rays. So when you say electromagnetic radiation, here you have X-rays, gamma rays, microwave waves, infrared and radio waves, and UV visible. Among this, the organic substance is absorbing only from a wavelength or corresponding frequency of the UV visible region. That UV visible region means ultraviolet and visible region is exceeding from 200 nanometers to 800 nanometers. That means 200 to 400 nanometer is ultraviolet region and 400 to 800 nanometer is the visible region. Okay. Now, this h nu is a quantum of light. What is this? A molecule absorbs a quantum of light. Quantum of light means a discrete quantity of energy proportional in magnitude to the frequency of the radiation. A discrete amount of energy. Energy is quantized, measured, or discrete amount of energy. How this amount of energy is sustaining? That amount of energy is proportional to the magnitude to the frequency of the radiation. Proportional in magnitude to the frequency of the radiation. So, a molecule absorbs an electromagnetic radiation of corresponding frequency UV visible region, and this region of light is quantized. Quantized means the energy of a quantity of energy proportional in magnitude to the frequency of the radiation. So E is equal to h nu, energy is equal to h nu, where h is equal to c by lambda. And all of us know these terms. Nu is frequency, lambda is wavelength, and c is the velocity of light. H is the Planck's constant. Since I'm handing to the PG students, I'm going little. A molecule absorbs energy from different wavelengths. Molecule can absorb energy from different wavelengths. Different wavelengths in the sense, if a molecule can absorb energy either from the radio frequency waves, molecule can have a freedom of absorbing energy from the microwave. This also can absorb energy from the infrared, ultraviolet, vacuum UV visible and X-rays and gamma rays. Now what happens? But in particularly in the photochemistry, the molecule is absorbing UV visible region. We will see why it is absorbing only in the UV visible region. But when a molecule absorbs energy from different frequencies, we are getting a different type of information. That molecule is undergoing different type of changes. As a result of the changes, that molecule will give us different information. Suppose if a molecule absorbs energy from the infrared region. Suppose an organic molecule is absorbing energy from infrared region. Imagine it is you are absorbing that molecule absorbing infrared radiation. So what happens? Because of this energy, that molecule is undergoing some changes. Most of the time when the infrared region means the molecule is undergoing certain vibrations. Certain vibrations. You know what is the meaning of vibration. Suppose if you take a spring, just compress it and leave it, then you can see a certain type of a vibrations. Same way, if you take in the microwave region, if you take a molecule is absorbing again energy from the microwave region, so the molecule will be vibrating. The molecule will be vibrating. Again, if a molecule is absorbing energy from the radio frequency, means there are some changes that can take place in the nucleus of the molecule. And if the energy is absorbed from the UV visible region, if a molecule absorbs energy from the UV visible region, that means here the electronic excitation is taking place. Electrons which are in the molecule will absorb energy and get excited into the higher levels. So, by now you could understand this organic photochemistry is very closely associated with organic photochemistry. Especially photochemistry is very close to the UV visible spectroscopy, which we have studied in our degree classes, which we will be studying in our detailed in the S3. Okay. So, to understand what is happening to the molecule and how it is resulting in the product, stereochemistry of the product, all these things we need to know certain important terminologies here. The first terminology what you need to know is what is electronic excitation. Then you should know what are different type of electronic transitions that are taking place. That means what are the different excited states that are present for a particular electron. And you also need to know what is happening, the chemistry of the excited molecule. You should know chemistry of the excited molecule. And fourth one is you also should know we will be studying all this transition with the help of a Jablonski diagram. Jablonski diagram. And we also will be studying again photophysical, that is fluorescence, and phosphorescence. So these are the certain important terminologies we are going to say now in details. Okay. Now the first one is what we are going to see. The first one is different type. What is electronic transition? What is electronic transitions? What type of transitions are present? Or an electronic excitations? Electronic excitations. The first one is an electronic excitation. Electronic excitation. So according to molecular orbital theory, we should know here the molecular orbital theory. If you are going to understand what is the electronic excitation. So the first topic what we are going to deal is electronic excitation. According to MO theory, we all of us have studied in our coordination chemistry and etc. What is MO theory? That atomic orbital, molecular orbital theory, atomic orbital combine together to form molecular orbitals which are equal to the number. Suppose if you have an atomic orbital of A and an atomic orbital of B combined together to form molecular orbital of AB of bonding, and same way molecular orbital of AB star, AB star, where AB is bonding and AB star is non-bonding. Non-bonding. So this is the basic of the electronic excitation. Now let us see. Suppose a molecule, organic molecule M, is absorbing energy H nu and get excited to M star and gives the product. Now there are two things that can take place. Either an excited molecule directly gives the product, that is called photochemical process. That's what we are studying here. Photochemical process. Now another thing also can happen. Sometimes the excited molecule, without going to give a product, will lose its energy and come back to become a reactant. And this is called a photophysical process. Energy of electronically excited states and stability of excited states can be explained by using Pauli's exclusion principle and Hund's rule. Energy of electronically excited states. Energy of electronically excited states. This is M star, which is electronically excited state, and the stability of this excited state. That means both energy and stability. Stability of M star we need to know, and this can be explained by using Pauli's exclusion principle and Hund's rule of maximum multiplicity. Now here are some important terms we need to know. Okay, suppose again come back, M0, that is in the ground state, absorbs radiation H nu. Okay, H nu. So now, for example, suppose a molecule in a ground state having two electrons. Then this absorbs energy. There are two things that can take place. The electrons which are in the ground state, after absorbing energy, can go into an excited state. And this can go into an excited state in two ways. One is spin retention. That means this is the electron and next electron, that is this is going here. The spin is retained. So this is called a retention of spin. Now another thing that can take place is one electron and the second electron, the spin inversion has taken place. So this type of excitation is called spin inversion. Now here you need to calculate the spin multiplicity. The spin multiplicity can be calculated. Okay, spin multiplicity, that is J. J is equal to module 2s plus 1. Module means either J value is positive or negative. It can be either or positive or negative, but we will be taking only as a positive only. That's what is called modulus. Only positive values will be taken. Now S is the spin, where S is the spin. spin orientation. These are basic quantum numbers, you know it, J. Now we will be calculating for each state what is happening. Suppose if you calculate for the ground state, molecule you are calculating. Here in the ground state, this one is a plus half and this one is minus half. So here S is equal to plus half plus minus half, that is equal to 0. So here J is equal to, for a ground state, J is equal to that is 2s plus 1 modulus 2s plus 1, which means 2 1 plus 2 0 plus 1, that is equal to only 1. When J is equal to 1, it is called singlet state. Okay, so denoted by S0. Since it is a ground state, it is S0. Again, let us calculate a spin orientation for retention of the spin. So in this case, what happens? S is equal to plus half. This is having a plus half, and here spin retention is taken. This is a minus half. So what happens? Plus half plus minus half is equal to 0. J is equal to 2 into 0 plus 1, that is equal to 1. Again, it is an excited state, so it is S1. Singlet excited state, that's why it is S1. It is an excited state. Now let us calculate here what is happening to the spin inversion. Okay, now it is a plus half here. Again, it is also plus half here. S is equal to plus half plus half, that is equal to 1. J is equal to 2 into 1 plus 1 is equal to 3. It is called a triplet state. When J is equal to 3, it is called a triplet state. Okay, so it is denoted by T1, excited state T1. So this is the main, what is this? Electronic excitation. When a molecule absorbs energy, it will be excited. That excited molecule only will give the product. Suppose the molecule in the ground state is having 2 electrons. According to the Pauli's exclusion principles and Hund's rule of maximum multiplicity, the both electron will be occupied in a single orbitals with an opposite spin. Okay, one will be carrying plus half charge and another one will be carrying minus half charge. Now what happens to the molecule when it absorbs energy H nu? Either two ways, retention of the spin can take place or spin inversion can take place. If the retention of the spin takes place, what happens here is it will be in a singlet excited state. J is equal to 1, so it will be singlet excited state. In the ground level also it is singlet state, but it is not in the excited state. Whereas if the spin inversion is taking place for a molecule having 2 electrons, then it will be in a triplet state denoted by the T1. Okay, spin multiplicity. Now what is happening here? Let us consider. Okay, always S2. That means, suppose again you are having a molecule. Suppose again you are having a molecule here. you have a ground state molecule with the two electrons. The molecule is excited with two ways. One is spin inversion is taking place. It is called S1. And here, for this same thing can take place, that is M star again. Here again you have another state, that is S2. And again the molecule is having two states with a spin inversion. Spin inversion. So it again T1 state, and again what happens? There can be another T2 state also. So always T2 will be greater than T1. S2 will be greater than S1. That means for a molecule, in a given molecule, there is not a single excited state, a single S1 matramalla. There can be possibility of T1 and T2 states and S1 and S2 states. Only that's what here we need to explain here. Now what happens to the molecule? Suppose if a molecule is undergoing, suppose energy of the molecules. Okay, this is a ground state, singlet. Here S1 state is there, S2 state, S3 state and S4 state. Energy is in the order of increasing. Now what happens here? The lifetime of the molecule is very important. To give a product, for a molecule to give a product or to become a product, the lifetime of a molecule in the singlet state and the triplet state, singlet excited state and the triplet excited state, how much time that molecule has a lifetime only will decide the product. So lifetime is very important to explain the stereochemistry of the product. Now what is this lifetime? When a molecule, now all of us know that S1 is the ground state. Okay, then what T1 is actually is having T1. That means if it is a triply excited state, it is T1 and T2, T3 and T4. Can see that triplet excited state is energetically less than a singlet excited state. So that's why T1 is much lower than the S1. The lifetime of, suppose here there is a molecule, okay, there is a molecule, absorbs energy and goes to M star. Here the lifetime of a molecule is 10 raised to minus 3 seconds. And the same molecule, if it is going here, S1 state, here the lifetime is 10 raised to minus 8 seconds. Now what is having more lifetime? Is it 10 raised to minus 3 or 10 raised to minus 8? It is 10 raised to minus 3. That's the way lifetime is S1. Singlet excited state 1 lifetime is very important to explain the stereochemistry of the product. And the lifetime is actually here 10 raised to minus 15 I suppose. 15. So what happens? The lifetime is actually T1 is less than singlet excited state less than singleted excited state S2. So the molecule is highly stable at T1, has a sufficient lifetime to be converted into product. So most of the chemical reactions takes place either at a T1 state or S1 state to become further into a product because of their lifetime of the molecules. S1 is the stereospecific reaction. Suppose if a product is coming from a singlet excited state, after suppose a molecule is going to the excited state in a singlet state, and if your product is resulting from the singlet excited state, and this type of products are actually stereospecific reactions. Stereospecific, a particular stereoform only, stereoisomer only can come. So they are stereospecific reactions. But if the product is obtained from a triplet excited state, they are now stereospecific reactions, either cis form or trans form, either Z form or E form, either R configuration or S configuration. Here it is stereospecific. Either you will get only S configuration, or only you will get R configuration, or you will get only cis form, or you get only trans form if the product is coming from a singlet excited state. Same way, if the product is obtained from the triplet excited state, they are non-stereospecific reactions. Now let us see the energies here. Energy of S1 is greater than energy of T1, isn't it? You see, S1 is greater than T1. Same way, energy of S2 is greater than energy of T2. Same way, energy of ESX, whatever it may be the state, is greater than the ETX. Now what happens? The energies between the S1 and S2, S3. S1 is less than, S2 is less than, S3. And T1 is less than, T2 is less than, T3. So that's why the products obtained from S1 and T1 are photochemical products. So according to the Hund's rule of maximum multiplicity, again according to the Hund's rule of maximum multiplicity, what this Hund's rule of maximum multiplicity says is, multiplicity increases, stability also increases. According to the Hund's rule of maximum multiplicity, if multiplicity increases, stability also increases. Generally, in photochemistry, the product is obtained from an electronically excited molecule in excited state. All the products I have mentioned you that. So let us consider the lifetime of the particle. At T1 is 10 raised to minus 3 seconds and S1 is 10 raised to minus 8 seconds. Every singlet excited state is corresponding to every triplet excited state. Every singlet. That means suppose you see here. See, every singlet excited state is corresponding to every triplet excited state. Okay, among the excited singlet state, T1 state is low lying energy state and all the photochemical reactions will be carried out at the triplet excited state. I have said all these things. So these are the main important topics of the electronic excitations. Okay, electronic excitation. Next we will be discussing types of electronic transitions and stereochemistry of the molecules, how you predict all these things. Thank you.